grades and they were spreading on the way, so I also could not come on time. I'm put on the board of Vista Foundation, but I came to know about the whole story after coming here, and it has been started by Professor Venkatesh of Belgavi and Professor Deshpande. Deshpande is not a professional mathematician or a physicist, but he has an enormous interest in mathematics and physics. I saw his library yesterday. I was really impressed. He collects many lecture notes and rare books, and he is genuinely interested. And these two people, Professor Venkatesh and Deshpande, they have started this foundation and they are willing to put even part of their life savings for promoting this foundation. And so I have decided to help them also to whatever extent I can. Now, this is a lecture series on history of mathematics. And so when the organizers asked me to give some semi-historical, semi-philosophical lecture on the development of idea of symmetry in mathematics. So I started thinking about that, and I've been thinking about this for all my life. But this opportunity gave me, this invitation gave me the opportunity to consolidate my thoughts on the subject. The idea of symmetry is universal and is inherent in human civilization from the beginning of human history. When we try to trace it in the context of mathematics, we immediately run into the deeper question, what is mathematics? Now, I will not define this immediately, and there is no definition offered of mathematics. We all learn mathematics, and in mathematics we are told definitions are important, theorems are important, corollaries are important, but nobody asks and nobody tells you what is mathematics. So the definition is not given, but of course there is some body of knowledge many of us consider as mathematics, and people sometimes just say mathematicians is what mathematicians do. That's of course a circular definition, but we take that and we try to arrive at a possible definition of mathematics. So I would like to take one issue which is relevant for telling you about the history of symmetry in the context of mathematics. This is a long debated issue. Is mathematics invented or discovered? How many of you have heard about this issue? Yeah, a fair number of people. You are all master students or?
A few master students, most of them are BSc students.
BSc students, okay. So, for master students probably I have heard this issue, and the BSc students also should appreciate these types of questions. Now, surely a lot of mathematics has gone into the sculptures of Ellora and Elephanta, or the paintings of Ajanta. And another famous thing for mathematics are the paintings of Alhambra in Spain. These sculptures or paintings are surely not discoveries. They are inventions of the sculptors or the painters. Now, in those paintings and sculptures, there is some mathematics, and in modern terms, that mathematics amounts to some subgroups of symmetries of 2 and 3 dimensional Euclidean space. They are implicit there. Now, are those subgroups, are they discoveries or inventions? The paintings are certainly discoveries and inventions. Are those subgroups, are they discoveries or inventions? Another example, take Kalidasa's or Shakespeare's dramas or poems. They are purely inventions. But now, Pingala, who wrote the Chandas Shastra, he is essentially using what in computer science now we call the binary system. He uses his binary system to explain the meters in poetry. Yamata, Raja, Bhanu, Salagam, those things. Now, is that binary system an invention or a discovery? This is the issue. To take a more sophisticated example, I will give you from mathematics itself. The Riemannian matrix or Wissler matrix, these were invented, I would say, by Riemann and Wissler, and that's why they are named after them, and they are very deep concepts. So, are those inventions or discoveries? Or still another example is mathematics like Edison's invention of an electric bulb, or is it like the pearls at the bottom of the sea, which mathematicians dive deep and discover? The underlying issue is, does human mind play any role in the construction of mathematics? True, the pearls exist, whether or not we discover them. But this is only an analogy. The question is mathematics like the pearls, in whose supposed existence the human mind plays no role? To say that mathematics is like the pearls, this is a position going back to the philosopher Plato, and is known as realism. The opposite view is that the human mind does play a role, and it's known as nominalism. Now, if you ask most working mathematicians, are you a realist or a nominalist? He is tight-lipped about it. He is just too much pressed for writing his papers and discovering or inventing some new things in his game. But if you, I believe that the mathematical community, if pressed to take a position, is probably equally divided among realists and nominalists. To get some perspective, let us consider a more general setup. This is the true game of mathematics. When we cannot solve a problem, we take a more general problem. More general problem may be easier to solve. So, let us take a more general setup and look at the process of what we call knowledge. All knowledge is based on experience. And experience generates thoughts. And a thought is given an expression. Now, yeah, you can, can I write it here? Experience, thoughts, expression. So there are these various experiences, call them E1, E2, etc. Similarly, thoughts, T1, T2, etc. And their expressions, so let me call it EX1, EX2, etc. Now an experience generates thoughts. So I construct this tripartite diagram. So experiences, I draw an arrow from experience to a thought if that experience generates that thought. But the same experience may generate more than one thought. And so this is not what in mathematics we call a function, it's just a correspondence.
Your voice may not be audible. If you are moving, you can use.
Why don't you ask the audience to be silent?
Yeah, hello. Can all of you hear me at the end?
Yes.
Without this?
Yes.
Okay, so there is no problem. Yeah. And now, different experiences may correspond to the same thought. A very wonderful example in science is, say, the gravitational theory and electricity magnetism theory. So both are connected with the thought of inverse square law. So very different experiences are related to the same thought. So there is also the arrow like this. And then thought is expressed in a certain way. So this is the whole process of knowledge. In mathematics, we restrict expression to a linguistic expression. Now, linguistic expression does not mean Kannada or Hindi or English. Mathematics has its own language, and that language is called set theory in 20th century. So, before that, what that language was also somewhat implicit. So this is the situation. Okay, so our what we call theories are the pattern recognitions in this tripartite graph, and which makes part of this tripartite graph comprehensible to us to some extent. This theory building is what mathematics is, at least in my opinion. Note that a theory is neither an experience nor an expression. Theory is a thought. It is neither an experience nor an expression. And this graph is, of course, time dependent. In each experience, the experience will be connected to a thought when someone thinks about a possible relationship. So from gravitation all the way to inverse square law, this is that thought was established after years of experience. So when an experience inspires a theory, the minimum requirement from the theory is that experience should be deducible from the theory. If there are two theories which can explain the same experience, the theory which explains more experiences is better than the other. Such thoughts inspired Aristotle to formulate deductive and inductive logic. I think in your college probably deductive and inductive logic is not taught, or is taught as a subject. When I was in college, it was a one-year course. But probably it will be so now, it is in that particular types of course will be only of some historical or cultural importance so far as I understand. Because the set theory, as it is being better and better understood and disseminated, I think in terms of that, all this deductive, inductive logic, that thought process will be explained in terms of set theory. Yeah, so okay, so this mathematics is really this theory building, and theory building is a thought. So the issue is what kind of thoughts that we may call mathematics. What kind of thoughts we can call mathematics. From ancient times, we have considered number as a category of thought which is characteristic of mathematics. How this idea evolved in human civilization is a really interesting chapter. A child has to go through this whole genetic process when it learns what numbers are. And it can do it only with some help from the elders. I do not think a child can discover all 0, 1, 2, 3, infinity on its own. It has to be told about this. So some animals are known to understand some numbers beyond 2. So many animals understand 1 and many. And they can understand 1, 2 and many. But beyond that 2, a few animals can understand. There are these experiments done in the psychology departments. The natural numbers, what we call 1, 2, 3, these are the thoughts generated by the experience of the counting process. But they already pose a very interesting question. You see, 10 flowers can generate the thought of number 10. Say 100 chairs can generate a thought of 100. But this does not explain the whole n, the whole set of natural numbers. We know, or what you may call that a dogma in present-day physics, that there are only about 10 to the 80 atoms in the universe. This is a large number, but still it is finite. It is finite in the same sense that the number of thoughts of an individual in a lifetime is finite. Or number of thoughts of all mankind is finite, because mankind consists of finitely many individuals. An individual can think of even 10 thoughts a second. His life consists of finitely many seconds. So the thoughts he can conceive of the time is finite. So in the same way, the whole set of atoms in the universe cannot account for natural numbers. The whole set of 1, 2, 3 going to infinity. And so n cannot have a natural material model. It cannot consist of any matter. So what is it? Now we all think we know 1, 2, 3 infinity. It is created by the human mind. In his famous paper of 1881, what are or what should be the real numbers? This is a famous paper in the history of mathematics. When it was actually written, I do not know whether the paper got accepted in a mathematics journal. It is a different type of paper. And so I think he published that as a monograph, he circulated it, and then it got, after some 20 years, people began understanding what he was saying. But in that, I should say about this paper a little bit more later.
So this is by Dedicate?
Dedicate.
Okay.
Yeah. So we think about the title of the paper. Not what are the real numbers, but what should be the real numbers. So even what real numbers are depends on your mind. It's not that they are given there, or these are the real numbers. And now in the same way, we cannot say that even the natural numbers, they are not there that, oh, this is the second atom, third atom. after 10 to the 80, that string is finished. And so even that set of natural numbers, even that idea is a creation of the human mind. So after Dedekind wrote that paper, this Kroneker's famous statement, God made the integers and all the rest is the work of man. Kroneker did not define God. In the Western thing, this is a dualistic notion. And actually these dualistic thoughts have generated all these questions, inventions or discoveries. So if this God exists, then this God is not made of matter. In my opinion, this God does exist, but it is another name for a collective, transcendent human mind. So it may not be a single human mind or just 10, 20 human minds, but it's a collective human mind which generates these thoughts or which organizes these thoughts. Now consider zero. In natural numbers there is no zero. So zero is to be added. Then negative integers. Now you all know negative integers. Many people in history did not know negative integers, by the way. So before 15th or 16th century, people did not understand negative integers. Then rationals. What is a rational? Do you know a rational number? How do you define it? Define it. It is a number of the type A over B, where A and B are integers. Not all real numbers are rational numbers. So this is the important issue in mathematics. So in the Times of India yesterday, the day before yesterday, there is an interesting cartoon. An ancient Indian mathematician is saying, before I invented the zero, I was nothing. Okay, it's an interesting cartoon. I think I'm not communicating the humor here. You please see that. I think can you possibly show that?
I have it in my system.
Okay. So you see that after the lecture. I just wrote this up a few pages, but I would like to expand it sometime later. And putting these pictures, etc. Okay, so before I invent, he also uses the word invented. Before I invented the zero, I was nothing. So this zero is an idea, is a thought. Nothing is an experience. The experience of nothing is also an experience. It's not nothing. And denoting it by zero is the expression. So the whole thing, and this whole thing is the beginning of a theory, and that theory is mathematics. The story continues. We find further objects like polynomial rings. Now, I'm sure you have thought, you have looked at the expressions 3x squared plus 4x plus 7, or 2x to the n, the general n, a natural number, etc. So those is the polynomial ring in one variable. Similarly, finite fields. How many of you know fields, the mathematical concept? Okay, so it's a set. Field is a set where you can define addition and multiplication, and they satisfy the properties which are satisfied by rational numbers. Particularly important is non-zero numbers have an inverse. And Galois, to whom we owe know a lot about symmetry in mathematics. Galois even found finite fields. Do you know finite fields? How many people know finite fields? You will learn them if you little bit continue with mathematics. And so such objects also have the properties of addition and multiplication and satisfying certain properties which are usual properties for the set of all integers. So these objects may also be considered in the number category of mathematical thought. We can go even further. We can consider an arbitrary set and consider functions in polynomial rings, say. So those functions can be added and they can also be multiplied. And they again satisfy similar properties. So such objects may also be considered in the number category of thought. And now what are these? These are all creations of the human mind. And the underlying thought process qualifies these objects as arising in the number category of mathematical thought. Even more abstractly, defining the notion of a ring, that is another notion in modern mathematics. So we will now consider the commutative rings with identity as a creation in the number category of thought. For most people, training in mathematics starts with introduction to the natural numbers and their additions and multiplications. But mathematics is not just repeatedly doing these calculations again and again. Most mathematicians can do modest numerical calculations reasonably well. But specially trained accountants in a bank or shops can surely do them better and much faster. And computers can do them even a lot faster. But that is not what we should consider mathematics. When we say mathematics, we do not mean such repeated calculations, but say definition of a prime. Definition or the understanding distribution of primes in this ordered set of integers, or equations involving numbers. They come under the number category of mathematical thought, and that is the subject matter of mathematics. Another important category of mathematical thought is space. It arises from our primary experience of the three-dimensional physical space. The Euclidean geometry of the plane is an integral part of our training in mathematics in high schools all over the civilized world. But note that Euclid did not define the Euclidean plane in his book. It's like the same thing, we study mathematics, but we don't worry about the definition of mathematics. Similarly, Euclid developed Euclidean geometry, but he never defined what is a plane, what was the plane for it. And it seems that he carefully chose to avoid the issue of what the real numbers are. So more on this I shall consider later. But with adoption of set theory as a language, we have considerably extended the idea of space. The set theory has given a new ontology to mathematics. Ontology is a word in philosophy. So before we start developing a theory, we have to make sure that we talk sense, and we have to decide on which objects we shall agree as that existing in our discourse. That is what ontology means. And ontology means a procedure to decide which objects we consider as making sense for our discourse. Before set theory was around, we basically allowed only sense perception in this as this decision procedure. The Euclidean plane exists because I can see something like a flat surface, and I can imagine that this surface extends on and on. So extends to infinity, quote unquote, what infinity means. So that is, that is what the Euclidean space for me. But with set theory in our armor, we can now assert any object as existing if it can be constructed out of the known sets by applying the elementary constructions, or call them actions in set theory, like if A is a set, B is a set, then the union of these two sets, axiom, it is also a set. Then the pairs, little a belong to A, little b belongs to capital B, then pairs AB, little a, little b, they also form the set. So these are the kind of axioms in set theory, which is called line set theory. There are also some set theories around. So the objects that can be constructed starting from known sets and by applying the procedure, the objects which can be constructed, that we now understand as the mathematical objects. So that those mathematical objects you may not be able to see or touch or smell. A very good mathematical example is the real projective plane. Real projective plane. We used to study projective geometry in my college days, and I think that was a good course. We enjoyed it very much. But that projective geometry, now with my later learning, I can prove that the projective plane, you cannot see that in your three-dimensional space. So does projective plane exist as a mathematical entity? It does exist because in set theory we also have relations, then something called equivalence relation, and projective plane can be constructed out of the two-dimensional sphere by identifying the antipodal points. And so that object exists mathematically, although I may not be able to see it. And similarly, when Einstein proposed his spatial and general relativity, he started talking about space-time, and that was a mystery for about 50-60 years in general public's mind. And now, even when we start learning it, we have to go through a certain process. But now, what is really space-time? We start with first of all real numbers, then 4 tuples of real numbers with some additional structure. That is what space-time is. So that's a very clear definition. So these are the two categories of mathematical thought, space and number. So I heard from my student days that space and number are these two categories which are characteristic of a mathematical thought. So I will just go a step further to arrive at a provisional definition of mathematics. So listen to this. Mathematics is a thought process created by the human mind to explain its experiences with the conceptions of space and number. So you can muse on that. I would like to have your comments on this. I mean, this is not the final definition or anything. I do not claim it to be. This is the provisional definition. You think about it. I repeat it again. It's a thought process. Mathematics is a thought process created by the human mind to explain its experiences using the conceptions of space and number. Now, people often ask, does space come first or number comes first? So even the mathematical community is divided into who starts doing numbers and equations in numbers, etc., and the other think in terms of pictures and so on. So whatever the group you belong to, you start saying, oh, that is that came first. So number came first or the space came first and so on. But if you try to resolve this issue from the knowledge process of experience thought expression, the answer seems to be to favor the space over number. We can see it if we observe how a child learns about numbers. It learns through stages. It first just understands one and many. Then with some more practice, it can understand one, two and many. And then much later, I think a child doesn't understand three right away. I think our the parents or anybody who teaches that child has to put it into his mind, 1, 2, 3, 4 up to 10, and reward him with chocolates and toffees if he can repeat the numbers up to 1, 2, 3 up to 10. And then somewhere in the process he comes to understand, oh, what does that 3 means? 3 means is a pair of triples. It is an idea generated by the pair of triples and so on. And you can see that in the development of human languages. The more ancient languages, that singular and plural that is expected, but there are also double. In Sanskrit there is Ramaha, Ramau, Ramaha. What is that? Ramau is 2 Ramas. So it is the same thing in Hebrew. And those things exist in even modern languages to some extent. But after the 1, 2, 3 was really understood, that we can separate these two and we say 2 Ramas. So the language got simplified. So for 2 Ramas, you use a different word. Then there was also declensions of words. 2 Ramas, go. So go in Sanskrit, gacchataha. Ramo gacchataha. A different declension. So singular and plural is certainly more fundamental, but this idea of double, originally it was expressed for each noun and each verb. There were different forms, and then the language got simplified when people understood the concept of 1, 2, 3. And so in that sense, I think that the space comes first before numbers. Now there is also an interesting thing when you learn your mathematics, you try to express that in terms of numbers because it's a very powerful expression. And you think mathematics is just numbers, or all the mathematical entities are numbers. So I think one thing we could take it from this talk, that not all mathematical entities are numbers, but most mathematical entities are not numbers. They may be expressible by using numbers, but they themselves are not numbers. So a very good example, take the notion of a vector. If you go to a physics class, they will say vector is a directed quantity. And they will say, okay, this is a vector, this is also a vector, that's also a vector, and so on. But now you see, when you take math courses, they will define vector is an element of a vector space. And vector space is defined with respect to a field. So first of all, you have to know a field. Idea of a field, and then idea of a vector space over a field, and then you prove a little theorem that vector space has a dimension, whether it is finite or infinite is another game. But if it is finite, then that this is well defined. So it is a set of elements in a basis. The number of elements in a basis is the dimension. And so you have to prove that if there are two different bases, then they have the same number. So that is the kind of thing that we develop the idea of a vector in mathematics. Are these two things related? Definitely yes. And then mathematical notion is much more refined and much more useful in accounting for different types of experiences. And so in physics, a vector is not a localized quantity. It can start anywhere like this. It's not localized. And we call it a quantity. Now, quantity is just a number. But then they also say directed quantity. So the mathematical vector is not directed, it's actually localized. So, but that is phrased in a different way, that in a vector space has a distinguished element, namely 0. Vector space is never empty. It has to have a 0. It's an abelian group. And abelian group has to have identity, existence. So with respect to that 0, so if I choose the origin and choose some basis, with respect to that basis, I can coordinatize the plane and express a vector by some, if the dimension is n, by n tuples of these numbers. But there, so you may start thinking, oh, vectors is just n tuples of numbers. But vector is not that. The original vector was just an element of a vector space. And these numbers, it's not in the nature of things of vector, what is called a vector. So these numbers are arising after you choose a basis, and so on and so forth. And so, I think I explained that, and you will see that most mathematical entities are not purely number. There is some combination of number and space idea. And it could be just space, it could be just numbers, and so on. So this example brings an important point into focus. The use of set theory for the expression of mathematics makes mathematics more precise, more refined, but also it can make it more complicated. But so set theory need not be the only expression for mathematics, for communicating mathematics. The expression in directed quantity that is used in physics is closer to visualization, closer to human intuition. It may be freely used in communication of mathematics, communication between a mathematician and a non-mathematician, between a teacher and a student, or between mathematicians of studying different areas. Even there, some shorthand expressions may be used which may not exactly adhere to the set theory. So this will increase the overall enjoyment of mathematics. As a thought process, mathematics can be applied to all our experiences. It has worked very well in theoretical physics, causing the Nobel laureate Wigner, a physicist, to wonder about the unreasonable effectiveness of mathematics. Mathematics seems so far away from actually matter that we deal in physics. So why is it effective? That is what you wonder. I shall try to explain that in terms of symmetry a little later. But actually mathematics has played a similar role in every theory building in natural or social sciences. So now you see mathematics also used in certainly chemistry, biology, etc. But it's also used in economics. Those who are studying economics, there are some notions of time series and so on. That's all the mathematics is used. So it is effective and can give conclusive answers as long as deep emotions like love, devotion, dedication or ethical issues are not involved. You cannot expect mathematics to solve an ethical issue. On ethical issue, people may have different opinions. While mathematics, which is true valued logic, it gives you only one answer at a time. So mathematics will be useful for everybody to learn, but not to give conclusive answers in your human situations. So I think my first talk is coming, 5 minutes, so that's wonderful timing. So let me end this discussion with a rather heavy example. Mircea Eliade was a distinguished professor of comparative religion at the University of Chicago. He actually he was first an actor and a journalist, but then he got his degree in philosophy from Professor Dasgupta, the old timer in Calcutta University. And then he turned to religion, turned to the study of religion, study of comparative religion. And he became a distinguished professor eventually in the University of Chicago. And he has done many field studies of religious thought in Indian tribes in America. He observed that in all those tribes, there are only two theories about life after death. You see, this is a heavy issue. But there are only two theories. One is the definite dead-end theory, that it stops and afterwards what happens nobody says. Or other is the reincarnation theory, it continues on and on. So he has extensively written on this subject. But in mathematical terms, it amounts to the following. Time is patterned over the real numbers. Real numbers is one of the really basic objects in mathematics. So time is patterned over the real numbers. On the real line, you have to choose some starting point. So that is, say, for an individual his birth, and then he says 100 years from then. So that is his real line made into real numbers in that way. And so his experience of time is like a interval on the real line. On the real line, I say, not real numbers. So locally, the human experience of life is that of an interval on a real line. That is a possible thought process arising from this experience is that life is a one-dimensional manifold, what we call in mathematics. A manifold. That's a very basic definition in mathematics. So I will not go into that definition right now, but it's a one-dimensional manifold. And it is an elementary theorem in differential topology that there are only two one-dimensional manifolds. One is an interval on the real line, and other is a circle. On a circle, you see, locally, this is a wonderful example of a what is called a manifold. That's a general definition that may come later in your studies. But say, consider an ant crawling along this. So what is the experience of ant on this? So it will see a nearby interval on the circle, but that interval is the same as interval of a real line. So globally, locally it looks like a real interval, but globally the structure is different. And so this and this, these are the only one-dimensional manifold. That's a serious theorem in differential topology. So that is what Mircea Eliade is really saying in mathematical terms. The definite dead-end theory corresponds to that interval theory, and the reincarnation theory corresponds to the circle. So an intriguing side issue here. Can one say that Professor Mircea Eliade actually reinvented a theorem in differential topology? In my opinion, a definite yes. And he explained a deep human experience. He not only proved this theorem, but explained a deep human experience. One does not have to be a professional mathematician to prove a theorem in mathematics. The only thing is that with more training in mathematics, one can reach such conclusions more quickly. And one will be able to express oneself more succinctly and correctly. It is recorded in American history that one of the great US presidents, Abraham Lincoln, took some time off to learn Euclidean geometry. This is about 1850s. He took some time off to learn Euclidean geometry when he decided to become a lawyer and enter politics. You know, Lokmanya Tilak was actually a professor of mathematics and knew enough astronomy to suggest a new calendar and dating system of the Vedas. It is not that well known, but actually true, that Mahatma Gandhi knew a lot of non-trivial mathematics, which may amount for his simplicity, directness, and extreme clarity in whatever he said or wrote. And this is, I met President Kalam a few times. We had at least 1 hour, we had a wonderful discussion. And he was an engineer by training, he is not a professional mathematician. He always wanted to know how you formulate things, what is new thing, etc. So he said that the mathematics that is actually used in firing the rockets is the mathematics we already knew in 19th century. So general relativity is not really needed even for firing a rocket. General relativity comes much later. And so that is the thing. So this is mathematics is after all a human activity. It depends on what kind of things you want to investigate and what kind of things you want to devote your time to. But it's a wonderful subject and you can devote your time to at least some time to mathematics.